Well, good morning, everyone. The end of the semester is so close, like we can almost smell it at this point. Um, so let's jump in. We're looking at some content from chapter 12 this week, looking at measuring the extent to which two variables are linearly related to one another. And the measure we use for that is the correlation coefficient, sometimes also called Pearson's correlation coefficient. So our first example today is just about developing some intuition around this. Because what will happen in practice is you're going to sample individuals or objects from some population, and for each sampled object, you're going to collect information from different variables. And so we're looking at the case where you have two variables, say an X variable and a Y variable, and you want to assess whether there is some kind of relationship between the two. So the typical way in which you're going to do this is start off by making some graphical representation. So you'll create what we call a scatter plot, where you denote each point represents, say, a specific measurement for the X variable and a specific measurement for the Y variable. So just say to emphasize that here, so we have a point here that corresponds to a specific X value, and it corresponds to a specific Y value. So for each XY pair, you can represent the points on a plot. And then looking at that graphical representation, you can often just visually see, is there some kind of relationship? Is it an increasing or a decreasing relationship? Is it reasonably assumed linear? And the correlation coefficient is the quantity that measures the strength of the linear relationship. So if we look at these four scatter plots that we have, the goal in each instance is going to be firstly determine if there is some kind of trend line that you could imagine running through the points. For example, if we look at the top left corner, I could very easily imagine a downward sloping trend line. And so that determines whether you're assessing a positive or a negative relationship in terms of the correlation coefficient. And then the strength of the relationship is determined by how closely those points cluster around the line. So if we just look at A versus C at this point, in each case, you can imagine a trend line. But if you look at how closely those points cluster around the trend line, in A, they're a lot closer. Where in C, they're a lot further apart. And so in terms of the number, if we just forget the sign, if we just look at the absolute value of the correlation, for A, you would expect the number a lot closer to 1. The closer you are to 1, the more perfect the relationship. In fact, if you had a scatter plot and you looked at the points on that, and they were perfectly lined up, so the trend line you imagine just perfectly runs through all of those points, that would correspond to a correlation perfectly equal to 1. So you only have a correlation of +1 or -1 if the points perfectly trace that line. So if we look through the list of correlation coefficients that we have written down here, and we're trying to match them up to the plots, I think reasonably you can eliminate -1 and +1 don't correspond to anything here because you have no points perfectly lined up on a trend line. 0 corresponds to when there's no discernible trend, Or perhaps you have something that looks like a trend, but it doesn't have a linear component. So I'll show you an example of that as well. But definitely in D here, like there's no reasonable way to draw one trend line over another trend line. Like those points are just a random scatter. Often what that means is if you look at how they cluster together, it kind of has a circular shape versus the ellipse we get, or the oval shape we get when the points follow a trend line. So in D, I would say we would reasonably expect that correlation coefficient to be pretty close to 0. Now, because this measures linear relationships, you can have an instance where if you look at your scatter plot, you may get some kind of perfect relationship, but there is no way to closely approximate that with a straight line. And so this is another instance where even though there's a perfect relationship, it's highly nonlinear. So we could easily expect the correlation in that instance to be close to 0 as well. Now, let's finish up A and C here. A, the points are pretty closely clustered to that line. And because it's negative, I would say reasonably it's negative 0.8. In C, positive, but not as closely clustered to the line. So choosing from the set that we have, I would say 0.4 is reasonable. So this leaves us with one more figure to identify here. And in this instance, if you look at what's going on, there's a strong possibility here that we have a nonlinear relationship, right? Like it looks like there's maybe some curvature on the left endpoint. That being said, in this instance, you could draw a trend line through this that is linear that reasonably approximates those points. So this is another instance where the trend appears to be nonlinear, but you can find a straight line that kind of approximates that curve reasonably well. Like it's not a perfect approximation, but the linear trend line does trace the points pretty well. And also, if you look at the cluster, those points even cluster pretty close to the linear trend line. So this would be an instance, you know, if I were asking this question on an exam, I'm not going to quibble about whether you pick 0.4 or 0.8 because of the nonlinearity. You could make an argument that it would be closer to 0.4. But there's definitely going to be some correlation that shows up here. But in point B, the importance is there's a nonlinear trend, so that correlation coefficient R is not an appropriate summary measure. Whereas in A, C, and D, the linear trend line does seem to be appropriate, and so it is a good measure of the relationship that exists between the two variables. Does anyone have questions here about 12.1? Now, I will not be so cruel as to give you figures like this and have you pick correlation coefficients out of a hat. I'm not expecting this. It'll typically be, here are a set of potential values, match them up as best you can with the figures that you see. But you should be able to calculate a correlation coefficient from data. Now, if we do this from scratch, if I just give you XY pairs, there would be a lot of work that has to go into that before you can do any of the calculations. So in our examples today, I did a lot of the pre-processing in that our first example here, it's based on a sample of 50 XY pairs, but if you look, pre-calculated are the sum of the X values, the sum of the Y values, etc. Quantities that are important if we're calculating the correlation coefficient. So in this first example, we're trying to find the correlation coefficient. And the first step in that is going to be calculating the sample covariance. Let me just adjust this pen. There we go. Sample covariance, we denote S subscript XY for the two variables. And I'll just write down the formula this time. It was in the lecture from yesterday. It's 1 over n minus 1, the sum of the product XY pairs minus the sum of the X's times the sum of the Y's over the sample size. So all of these quantities have already been calculated. This will be 1 over 49. Sum of the XY pairs, pair products is negative 34.428. Sum of the X's is 1.104. Sum of the Y's is 1.188. And so if you just go and punch all of this into your calculator, your sample covariance is negative 0.703. Now, to get the correlation is going to be the sample covariance divided by the square root of the product of the variances. So we also need our sample variances. But we have what we need. Now, this is a bit of a throwback, but hopefully you remember the sample variance, say for the X data, is given by 1 over n minus 1, sum of the squared X values minus the sum of the X values squared over the sample size. So in this instance, this would be 1 over 49 times, we have the sum of the squared X values is 32.93. We have the sum of the X values, we can square that and divide by 50. And if you do this, the sample variance for the X data is 0.672. Now you're going to do the same thing for the Y data. Sum of the squared Y's minus the sum of the Y values squared over the sample size. And this value is 1.27. So this now gives us what we need to calculate the correlation coefficient, which in this case will be negative 0.703 over the product of these two sample variances, square root. And this ends up being negative 0.761. The question also asks you to interpret, and this is where we had a rule of thumb in the lecture yesterday to help you determine whether to classify something as a weak, a moderate, or a strong correlation. In this case, our correlation is between 0.5 and 0.8 in absolute value. So that would be classified as moderate or moderately strong. And you also have to give the direction, it's a negative correlation. And you can always add to the problem the caveat of saying without a visual inspection, it's not possible to determine whether a linear correlation coefficient is the most appropriate summary measure. But if it is, this qualifies as a negative and moderately strong correlation. So we have another calculation example. So let's run through the next one, and then I'll check if you have any questions. On this one, I did even a bit more pre-processing. I didn't leave you to calculate the variances on your own. You'll see here, you already have the sample variances, because otherwise these calculations can just get pretty tedious. In this case, our sample size is 22. That's how many data pairs we have. So to get to our correlation, we need to calculate the covariance first. And I'm just going to plug the numbers into the formula this time. Now, do note here, we need to, at this point, subtract the product of the sum of the x's times the sum of the y's. But we only have the average x bar, so the sum of the x's can be calculated as the sample size times the average. Right? So to get the sum of the x's, it would be 22 times the average. And sum of the y's would be 22 times the average of the y values over 22. So just finishing out this calculation, the covariance you'll get is 1.97. So at this point, we can calculate the correlation coefficient. Take that covariance divided by square root of the product of the variances. And in this case, you'll get 0.931. So here, when you're interpreting, the rule of thumb is if the absolute value of the correlation exceeds 0.8, it is classified as a strong correlation. So it's positive in direction and it's strong. So there is your interpretation in this instance. Again, at this point, when the correlation is this close to 1, it becomes a little bit difficult to imagine nonlinear relationships that result in a measure that's close to, very strong positive correlation. It's not impossible, but the closer you are to 1, the more implausible it becomes that it's some nonlinear relationship. But again, perfect world, you would really like to see that cloud of points, the scatter plot for the data. So does anyone have questions about calculating correlation coefficients as in 12.2 and 12.3? Okay, let's move on. So the next topic that was covered in the lecture then moved into testing hypotheses about the correlation coefficient. And specifically, we looked at 2 different tests. One of them is testing if the correlation is equal to 0. One of them looked at testing whether the correlation was equal to some other specified value that was not 0. In today's examples, we're only going to look at testing for a 0 correlation. So here we have a sample of size 18 from a bivariate normal distribution. And that bivariate normality is important. We're going to use a t-distribution here, but the t-distribution is only valid if your original data come from a population that is bivariate normal. again, just a recap of what that means. It tells you that if you look at each of the variables individually, if you just look at the population of X values, it'll follow a normal bell curve. If you look at the population of Y values, that will follow a normal bell curve. But it goes beyond that, because if it's bivariate normal, the only way they can be related to one another is linearly. So it also imposes a linear structure if we look at them jointly. It doesn't tell us how strong that is. That value can still range anywhere from -1 to +1, but it does restrict us to only having a linear structure if we look at them jointly. So bivariate normal is a very important assumption if we look at how this test plays out, especially for small sample sizes. And sample of size 18, we would consider that a pretty small sample size for estimating correlation. So sample size of 18, we go through the steps of calculating the correlation and find it's 0.312. We now want to test the null hypothesis that the population has a zero correlation against an alternative that says the population has a correlation that's larger than 0. And we want to do this at the 5% level of significance. Now, the test statistic that we use here, we denote it by big T, and it's calculated as the square root of sample size -2 times the observed correlation coefficient over the square root of 1 minus the correlation coefficient squared. So in this instance, that would be square root of 16 times the 0.312 over 1 minus the square of 0.312, all of that square root. And if you go and do this calculation, this t value is 1.314. Now, the reference distribution for this test is a t distribution with n-2 degrees of freedom. So in this case, t distribution with 16 degrees of freedom. Our observed statistic is 1.314, and because our alternative is that the correlation exceeds 0, that exceedance tells us we calculate our p-value only by looking at the tail area to the right of the observed statistic. So calculation of p-value in this case, if we use the TCDF function, that typically gives us area to the left, although I guess we could set it up and say we're just calculating our TCDF. We want area from a lower bound of 1.314 to an upper bound of infinity. You'd put in a large positive number there, and your degrees of freedom would be 16. And if you do this calculation, you get a p-value of 0.104. So the p-value in this case exceeds the 5% threshold, so we do not reject the null hypothesis. What does that tell us? The sample does not provide any evidence that the correlation is larger than 0. The population having a 0 correlation is consistent with what we see in the sample data. So that would be a conclusion that you could draw here. If you had more context, if you had specific variables you would interpret it as saying there's no evidence that these two variables have any linear correlation to one another. Now, there's a part B to this problem, and all that does is it increases the sample size to 38. And we're trying to see what would happen to this test if we had the same sample correlation, but it had been obtained using a larger sample size. In this case, more than twice the sample size, right, from 18 to 38. So our test statistic in this case will be square root of 36 times 0.312, again, square root of 1 minus 0.312 squared. And in this case, we have a value of 1.97. Now, p-value obtained in the same way, except now we're using a t-distribution with 36 degrees of freedom. Our reference value is 1.97, but we're still doing area to the right of that as our p-value. And so in this case, if you do TCDF, lower bound 1.97, upper bound infinity, degrees of freedom 36 in this instance, you get a p-value of 0.028, which is less than the alpha of 0.05. And so in this instance, you would reject the null hypothesis. Now, I ran out of space on this page, but you would also add an interpretation that says sample evidence is consistent with having a correlation value larger than 0 or having a positive correlation value. That would be how you interpret it in this instance. Any questions about this testing problem? We have one more example similar to this that we'll look at.
Dr. Potgieter, could you repeat the justification you just said?
Yes, so your conclusion here would be, you want to state something that, because you're rejecting the null hypothesis, is going to be in line with the alternative. And the alternative here said the correlation is greater than 0. So your interpretation would be that the sample evidence is consistent with having a positive correlation value. I'd prefer at that point you write it out in words, but just crammed in rho greater than 0, so positive correlation value.
Thank you.
Yeah, so one more example here that we can look at. This one is referring back to 12.2. Important information just to have from 12.2, or the only relevant information, is we'd calculated a correlation of negative 0.761, and we had done that using a sample size of 50. Now, the problem never stated anything about normality. So the only way we can do this test is we need to assume the sample was obtained from a bivariate normal distribution or bivariate normal population. So keep an eye out for that kind of thing if I ask you about assumptions you need to make for your inference to be valid. But now we have what we need to test our null hypothesis of a zero correlation, in this case against a two-sided alternative. So test statistic T going to be square root of sample size minus 2 times your correlation value over square root of 1 minus the square of the correlation value. So in this case, we have a value of negative 3.42. So our p-value in this instance, because our alternative is two-sided, we need to consider both sides or both tails of our t-curve. We're using a t-distribution with 48 degrees of freedom. And our p-value corresponds to the area in both tails now. So we're essentially calculating what would the probability be of having a correlation this extreme or more extreme if the truth were zero. And so the p-value in this case, we can, for example, calculate it as 2 times just evaluating one of the tails, so lower bound negative infinity, upper bound negative 3.42, and 48 degrees of freedom. And if you do that here, you're going to get a p-value of 0.0012. Now that's a pretty small p-value. So it does, at first glance appear that there's evidence against the null hypothesis, except we're evaluating this at the 0.1% level of significance. 0.1% means your alpha is 0.001. Because you have to divide by 100. So our p-value of 0.0012, that's larger than our alpha value of 0.001. And so we do not reject the null hypothesis in this instance. So our conclusion will be the sample evidence is consistent with the population having no linear relationship. In other words, rho equal to 0. This is our conclusion at the 99.9% level of significance. So admittedly, we set a pretty high bar in this instance. People rarely do inference at this higher level of significance. But what you could easily say in this instance is, well, our sample correlation coefficient, that's a pretty large value, negative 0.76. It's close to that threshold of going from a moderately strong to a strong correlation. And so if you're worried about making a type 1 error here, making a type 2 error, not rejecting when you should be rejecting the null hypothesis, you can always advocate for going back to the drawing board and collecting some extra data. That's always an option in any situation. So are there any more questions about these example problems? So I have a question about the use of the t-distribution. If you have a problem, if your null hypothesis is testing whether the correlation is 0, and you have a bivariate normal distribution, you will use a t-distribution to evaluate that. If you watch the lecture from yesterday, and we'll get into examples of this on Thursday, there are instances where we use the normal distribution, and it's still testing about a correlation, but it will be testing for a value different than 0. So as long as this is your null hypothesis, correlation equal to 0, you will use a t-distribution with n-2 degrees of freedom as a reference. So I'll wrap up the recorded segment here just by saying no new posted lecture tomorrow, because we still have several example problems I want to do related to the lecture from yesterday. So if you haven't watched that yet, make sure to sit down and watch that. But there won't be a video tomorrow. There will be a live session on Thursday working through some more example problems looking at correlation.